Hello, I'd like to talk a little bit more about sampling distributions and what is it all about really. Basically, sampling distributions are used to determine probability. If you remember in the last chapter, we talked about a random trial, which is something that you do that creates some random outcome like rolling dice, things like that. So back in chapter 10, one random trial we had was rolling dice, and we wanted to know what's the probability of getting the sum of the dice being greater than 7 and things like that. And to answer those sort of questions, we looked at a sampling distribution, and the sampling distribution looked looked like this. For rolling 2 dice, there's 36 possible outcomes. Well, and then you use this sample space, excuse me, to come up with all the different um, probable outcomes, and you can count how many ways can you get 11, how many ways can you get 7, and so forth. And you can ascertain the probability of certain events occurring. Now, we're doing the exact same thing, but with the random trial now is taking a sample. And so, like the example with drawing fish from a fish tank, um, there's many more than just 36 possible outcomes. So taking a sample and then computing uh, x bar. Okay, that's our random trial, and that is random. The whatever you get from x bar is different every time. And so we want to answer questions like what's the probability that a particular x bar from a sample is going to be greater than say 5 milligrams or something like that. How do you figure that out? Well, instead of looking at a chart like this for dice, we look at a sampling distribution. And so the sampling distributions we've encountered so far have been normal curves. And so you look at the sampling distribution, and that is kind of like your chart of all the 36 outcomes, except this is uh, a, a distribution of all the possible x bars. And so we use sampling distributions for two main reasons. So here's the reasons we use sampling distributions. Reason number one is to figure out uh, the probability of x bar being greater than something, less than something, between two numbers, and so forth. Whatever it is, what specific instance you're looking for, that's the first reason for sampling distributions. And so if we want to know the probability that x bar is greater than 5, we have to figure out, well, where is that on here? If let's say the mean is 3 or something, what's the probability? Once you know your standard deviation, you can figure that out. What is that area where x bars are greater than 5? Just like back to our dice chart, if we want to know what's the probability of x being greater than 5 on here, we have to shade in the region or circle the region where all the x's are greater than 5. So like 5 and 1, 5 and 2, and so forth. Now the other reason for dealing with sampling distributions is to figure out margins of error. Because we can make statements like, because our sampling distribution is in many cases a normal curve, we can make statements like 95% of x bars are between such and such and such and such, because the 68, 95, 99.7 rule, between blank and blank. And so which is two standard deviations, whatever those standard deviations turn out to be. And so you can make statements like that, and then you can say, well, 95% of the time, our particular sample mean will be between two certain numbers, which means that your sample mean, you can rephrase this another way here, that your sample mean will be within two standard deviations of whatever the true population mean is 95% of the time. Okay, and that's a very powerful statement right there. And so once you know what is two standard deviations, even if you don't know the real population mean, which you're not going to know, but once you know the two standard deviations, you've got yourself a margin of error. And that's another big reason for sampling distributions. And that's what sampling distributions are all about.